Hello class, this lesson we're going to learn how to apply the angle bisector theorem. First, I'd like you to write down a definition for an angle bisector in your own words, and then I'll show you my definition. So an angle bisector, it's a ray, it could be a segment or a line as well, but it cuts an angle such that the two angles that it forms are congruent to each other. So when we're labeling that in a diagram, you draw those little arcs on there. So here's an example that has an angle bisector, and it has lengths measured here for us. What do you notice is special about those lengths? What relationships do you see there? Well, one relationship is that if you divide BD by CD, that's 2. And that's equal to what you get if you divide BA and CA, that's also 2. And that's important because that is an example of our big theorem for today, the angle bisector theorem. So if you have an angle bisector, it splits the opposite side into 2 segments. And the ratio of those 2 segments is the same as the ratio of the corresponding adjacent sides. So if we take BD and divide that by CD, let me do it with highlighter. BD is in the larger triangle, and so is BA. CD is in the smaller triangle, and so is CA. So if we divide BD, which is a piece of the segment that's being split, by CD, that's going to be the same as BA over CA. So let's see why that is true. To complete the proof, first we're going to construct this line parallel to AB that passes through C. We know there's exactly one line by the parallel postulate. And that's going to cross the angle bisector at some point. Let's call that E. The goal is to show that triangle ABD is similar to triangle ECD. Because then, once we know they're similar, we can write a proportion. And hopefully that proportion will help us get to what we want to show, this one from the angle bisector theorem. So how can we show that those 2 triangles are similar? So let's highlight them. We're looking at triangles ABD. So ABD in blue. And ECD. E to C to D. Why is the blue triangle similar to the red triangle? What do you notice there? Well, remember we constructed this line a special way. Draw our chevrons on here. These are parallel. That was by our construction. What do we know we get when we have parallel lines? The alternate interior angles are congruent. So one pair of angles congruent. And what do we need? Another pair of angles, right, to get angle-angle. And we have vertical angles right here that are shared. So by angle-angle, those are similar. Let's go to that argument down here. So this is just an explanation of what we just talked about. And now, if you look at this diagram, since they're similar, we have BD divided by CD, that's the same as BA divided by CE. That's close to what we want to show. There's a difference there, though. What we want to prove is the second proportion written down here. The difference is that we have a CA here and a CE from our current proportion. How can we fix that? What do we have to prove in order to solve our problem? We'd have to show that CE equals CA. So what do you notice about segments CE and CA? What's special about them? Well, they're both parts of a triangle. They're both sides of a triangle. But what type of triangle are they the sides of? They are sides of an isosceles triangle. In particular, they are the legs. And we know by the converse of the base angles theorem that the legs are going to be congruent because the base angles are congruent. So this is an explanation of what we just said. And so now if you just substitute, plug that into the original proportion that we wrote, you get what we wanted to prove. BD divided by CD equals BA divided by CA. So let's actually apply that theorem now. Here's our first example. We're going to walk through this one together. When you practice 2 on your own, and then check your work with mine. Then we'll go to our final example. So here are our sides. The angle bisector cuts this side. That has a length of 15. We want to figure out what the lengths of x and y are, or what the measures of x and y are. So what can we write? Well, if we apply the angle bisector theorem, we know that y divided by x is going to be 12 divided by 8. But this is one equation with 2 unknowns, so we need another equation to solve that. We need to write a little system. So what other equation can we write that's going to be helpful? Well, we know if we add x and y together, we're going to get 15. So x is just 15 minus y. Just subtract y from both sides. If you had written another equation using the angle bisector theorem, we won't be able to solve that system because we'd have 2 equal equations. So we need a totally separate equation. And now we can substitute. So first, before we substitute, we're going to do cross product. You can substitute first if you wanted to, but you don't have to. Now we're going to plug in for x, apply distributive property, move all your y's to the same side, plus 12y on both sides, divide by 20, and you get 9. So y is 9, and to figure out x, it's 15 minus 9, which gets us 6. So those are missing lengths, and here is the explanation. Just verbalizing what, just writing down what we just verbalized together. Example 2 is very similar. You're going to get some fractions, so just be mindful of that. So try this, and then I'll show you my solution. So to solve this one, it's really the same process. You have to write 2 equations. And in this one, a little bit different. We substituted before cross product. You're going to get the same answer. Just make sure you distribute correctly. That's probably the biggest mistake. And we end up with 96 over 23, which is 4 and 4/23. We substitute that into our original equation, and we end up with 7 and 19/23. So they're showing you can write these as mixed numbers or improper fractions. You can write them as decimals as you want, but note that you can't write out their whole representations. So just make sure you put ellipses after a few digits of decimal. Try this one the same way. Very similar idea. So here are the 2 equations you can write. Use the cross product, substitute, distribute, move your x's to the same side, divide by 27, and you get these numbers. Or this number just in different forms. Substitute for x, and there's our answer. Now this last one is a little bit different. In this case, they give us the lengths of the side that's split, and they give us the perimeter of the triangle. So how can we figure out what the lengths of these 2 sides are of the triangle? Well, there's two ways to solve this. I'm going to show you the way that corresponds to how we've been doing the other problems. And there's kind of a slick, shorter method we could use. So we don't know what these lengths are, so let's call them x and y. What equations can we write that involve our variables? Well, we know that the perimeter is 33. So if we add everything together here, we get 33. And then I wanted to solve for x because we're going to have to substitute. Another equation we can write involves the angle bisector theorem. So x over y is 5 over 6. Use the cross product, and then substitute for x. Distribute. Move your y's to the same side, and you get 12. And then finally, we would substitute, and you find out that x is 10. So this is the way of solving it like we did the other problems. But there's a little shorter way we could have done this. We could have written these sides using the same variable. We know that they have the ratio of 5 to 6, or 6 to 5, depending on how you're looking at it. So we just don't know what factor they're being multiplied by. So let's call that factor z. And now we know if we add up these 4 measurements, that's the perimeter. So we just have one equation with one unknown. So you solve this and you get z equals 2. To figure out the 2 missing sides, you substitute for z. 5 times 2 is 10. 6 times 2 is 12. Those are the same answers we got before. This way was a little bit shorter. In this lesson, we learned how to apply the angle bisector theorem. Thank you for watching this video.